class. Adam Ward here. Our first video in our lecture on sort of pipe flow potpourri, a handful of random topics if you're going to be thinking about systems of pipe flow. This first video is going to cover minor losses. So we've talked in the past about major losses due to friction. So today we'll cover minor losses. Learning objectives for this recording, as well as those that accompany it, are listed here. And so we're going to be able to deal with minor losses, non-circular ducts or pipes, so elliptical, rectangular, for example, and we'll know how to deal with pipes in series and pipes in parallel. Okay, so what do we mean when we talk about minor losses? And I think the best way to do this is with a visualization out of IIHR out at the University of Iowa. So let's hit play on their video.
A change in the pressure field as a whole is provided by the introduction of guide vanes. These can be made to conform to the original boundary and thus increase the relative radius of curvature locally, or else the whole structure can be redesigned accordingly, as in the case of this miter bend. The flow is obviously much worse without the vanes, but much more efficient once vanes have been installed.
Okay, and so what I really want to point out to you here is up near the apex of the pipe, so the top part of it, and just to the right side of the corner in the bottom, you can see this, these recirculating eddies, sort of turbulence happening within the pipe. So that is not about regular pipe flow. That's not well described by our turbulent pipe flow equation. Those are additional losses. And so things like we just observed in the video here, these are energy losses that are associated with any other motions, typically when we force streamlines to turn, or when we take that flow and we transition it from being fully developed into a developing regime, and we've got this extra energy requirement. All of those things will get lumped together for us in minor losses. So what this looks like sort of in an ideal world, so if we look at the image across the top, and we label our energy grade line and our hydraulic grade line in the solid black, the reason that hydraulic grade line is shown declining with a constant slope is friction. So that's energy loss per unit length of pipe. In contrast, in the bottom diagram, you notice that in green is labeled this HL minor, or head loss minor. And that's depicted here as a step change at the location where we have a valve. So that what I've circled in green along the pipe there, think of that as a valve that might be able to control the flow. And so these minor losses are localized to where a valve or a fitting or a bend in a pipe is, and they manifest by taking that friction slope and causing a step change in it. So instantaneous energy loss at the point where this fitting exists. Now, we're pretty well set up to deal with these already. And so what you see I've written here is just our Bernoulli equation. So point 2 on the left, point 1 on the right. And we've talked in past lectures already about how we should account for major losses. And minor losses are going to go in a very similar way here. So we're going to represent minor losses with this new term that I've underscored in blue, minus capital KL. So think of that as a coefficient to describe head loss times velocity squared over 2g. And that would be whatever the velocity is through that fitting or bend or valve in the pipe. And those KLs are empirical coefficients. So I've grabbed a table out of the textbook we're using in my class. You can see, for example, depending on if it's a 90-degree or a 45-degree bend, if it's a short radius or a long radius, if it's threaded or not threaded, down in the bottom section, valves. So for example, if you've got a gate valve, just having the presence of that gate valve, where it says gate fully open, so a valve, even if it's not slowing down the fluid, it is tripping up the flow and you're getting minor losses. And then as you increasingly close that valve, those head losses become substantial. Okay, so for these minor loss terms, we're going to look up these coefficients in a table. And of course, it is quite possible that you don't have a pipe system that's just got one of them, but it has multiple fittings, bends, or valves in it. No problem. We can just add those coefficients together and use them in the equation we saw on the previous slide. So for example, if we had a reservoir of water with a valve in line and then a 90-degree bend, we would have an entrance loss circled in red, we would have a loss at the valve in green, and we might have a loss at that 90-degree bend in purple. So anytime that you're making flow do something other than be fully developed flow, you're incurring some minor losses. And those are just additive along the flow path. So let's look at one more example. Not shown on the previous table is the idea of an inlet. So when we take flow and we accelerate it from functionally still in a reservoir to flowing through a pipe, here's two extremes shown on the right hand side. So a sharp inlet, like we're looking at on the top, what happens is you get this contraction of flow and you get what's called this vena contracta, and you get these little regions of recirculating eddies. Those are exactly what you observed when we watched flow go around the 90-degree bend in that video clip that I showed at the beginning of this recording. So those recirculation regions are functionally wasted energy. They're energy that goes into turbulence rather than moving flow where we want it. And so you get an entrance loss. Now, if you smooth that out by rounding off the corners, as shown in the bottom, you get a much smoother transition as that flow accelerates. You eliminate those little areas of recirculation, and you're more than an order of magnitude smaller in energy losses. Right, so small differences in the design of these fittings or pipe systems can make a big change in how much energy is available to move fluid. Let's do an example to this effect. So here we've got a reservoir. We've got a change in elevation of 40 meters between the two given points. We have a sharp entrance. We have a open globe valve, and we're given the KL for both of those, a flow rate, and we're told cast iron pipe, 125 meters of it with a 5 centimeter diameter. Over at capital T is a turbine, and so the question here is, what's the most power we can pull out of the system? So just to be clear, this sharp entrance, that's making the water turn the corner to accelerate, and the globe valve shown in green. And so what we're after is the circled in purple turbine and how much power we can extract there. So we can go ahead and write our energy equation. Point 2 on the left-hand side, so the downstream point equals the energy we have at the upstream point, P1 over gamma plus Z1 plus V1 squared over 2G. Then we're going to subtract off the head that the turbine removes, HT, and head losses associated with both major and minor losses in this problem. Well, we've got a free jet over on the right-hand side, and so pressure in a free jet and pressure at the water surface are both 0. We'll get rid of those. Pick our datum down at Z2. So our Z2 goes to 0. And velocity at 1, shown in green there, goes to 0. That's the velocity out in a tank. So with those simplifications, now we can organize, and I'll go ahead and let that play out. So what I've done here is I've taken our energy equation, dropped off some terms, and then I've reorganized it to solve for the turbine head, because that's part of what we're after here. So I get head for the turbine, HT, is equal to Z1 minus, and then you'll notice I factored this V squared over 2G out of several terms. And so just to point out where those come from for you, this first chunk of it, the 1 inside the parentheses, that's accounting for the actual velocity head at point 2. You can see I've used yellow in both equations to kind of make that connection for you. For major losses, we've got our friction factor F times L over D, and then normally we'd have times V squared over 2G right in that chunk. I've factored it out in front of the parentheses, and I did the same thing for minor losses. So I've gone ahead and solved our energy equation for turbine head, and what we're left with then is actually doing the math here. So starting down this road, Z1 was 40 meters. We know there was a 40 meter elevation change that was given, minus, now V2 squared over 2G. Where did I get V2 in this problem? I used our knowledge of the pipe diameter and the discharge to solve for a velocity of 2.04 meters per second, shown in red. Inside of the parenthetical here, a 1 that stays. Now for our major losses, you'll notice I've plugged in for F 0.0316. That's a Moody diagram problem. So we were given that this was a cast iron pipe, we were given the diameter, and we have enough information to calculate Reynolds number, and epsilon is a value we can look up for cast iron. So I've gone ahead and used the Moody diagram. We've practiced this in past lectures to get that friction factor F. 125 meters of pipe in the numerator, a diameter of 5 centimeters or 0.05 meters down in the denominator. And then finally for minor losses, you'll see I've got a 0.5, and that accounts for that sharp corner transition. And so my 0.5 is accounting for that first transition, and that 7 is accounting for the valve. And so we can just add both of those in. Yep, so for KLs for the entrance and valve. And so in this problem, what we find is the turbine might remove as much as 21.5 meters of head. Now that's not what we were asked for. We were asked for the power the turbine could generate, and so this is just to remind us all how we convert head into power or work rate. So specific weight of water, 9,810 newtons per cubic meter, multiplied by the head for our turbine, 21.5 meters, and our discharge of 0.004 cubic meters per second. And I get a work rate or a power of 840 watts that this could take out of the system. All right, folks, I hope this gives you a sense of what those minor losses are, where they come from, and how they fit into our energy equation problems. I'll be back with a little more potpourri on pipe flow in the next lecture video. Thanks for sticking with me, all.